the fundamental question in phonology and language acquisition. How do children learn their languages, especially phonological knowledge from the real world, especially the noisy real world data? By the end of the talk, I want to convince you that phonological learning can be achieved with two essential ingredients. The first is called restrictive hypothesis space defined by homolanguage theory. And the second is called exception filtering mechanism. In particular, I propose a hybrid model that combines the strength of the traditional categorical grammars and statistical criteria and borrow from the probabilistic models. Yeah. Let's first take a look at the phonological knowledge in our textbooks. Say all appear exception-free. There are two major types. The first is called the phonotactics, which means the speaker's knowledge about the permissible sound sequences. For example, English speakers least favors the sequence like BN and SFA sequence. So you cannot say, if you give them a novel form like benek, speed, they will judge them as unacceptable. Another type is called alternations. Of course, means the distinct realizations of underlying representations. For example, English plural morpheme can be realized as the, voices the, and also other forms. We can test this knowledge in the famous work test. Okay, the plural morpheme is realized as a voice the after the g. So these are the knowledge that we're dealing with in this research project. And our textbooks paint a exception-free picture, very elegant picture of phonological knowledge. But in the real world, as Edward Sapir would say, all grammars leak. So there are many lexical exceptions to the phonological knowledge that we know, like the BN penalization of BN sequence has no exceptions in English, but the SFA sequence, it does exist in some English words. This table shows you this tension between the lexicon and the grammar. Not every word that follows the grammar is in the lexicon. Like black is a possible English word. It follows the English. It doesn't violate any onset phonotactics in English, but it does not exist in English lexicon. There's also those words that are in the lexicon but violate the grammar, like sphere. It violates the SFA phonotactics. So the challenge emerges from this mismatch between the testedness and the grammaticality. And the learner must infer the grammar while storing those lexical exceptions that violates our phonotactic grammars. And here are some more exceptions in English phonotactics, many of them from other languages. They all sound exotic, as what people refer to in the literature, like schmuck, slotty, etc. And these not only exist in English, but also found in many other languages, like in Turkish vowel harmony, the regular pattern disfavors the two vowels with different backness feature. So your front vowel cannot follow another back vowel, but there are exceptions from other languages like English, Arabic, French that does violate these regular patterns. Despite the existence of those lexical exceptions, children learn those knowledge at relatively young age. Like Turkish kids learn their phonotactics as early as 6 months. English kids become sensitive to their onset phonotactics as early as 8 to 10 months. And the learning of alternations are a little bit later than that, also very early as 12 months. How do they do that? That is my research question. And what computational modeling can do is to provide a testing ground for our theories of phonological learning. For example, we can ask what kind of information or structures that children must keep track of or filter out during phonological learning. We can simulate a linguistic experience using the real-world corpora, like the famous child-directed corpora that are available for us today. And we can train the computational models to learn a grammar that predicts the human judgments in behavior experiments, and this will help us to understand the language acquisition process. And I believe this connection is bidirectional. Okay? Understanding the language acquisition of children can provide insights into the general problem of learning, how any machines, any device can learn and achieve the human level intelligence from the real world data. It will help us to build better machine learning models, just like studying how birds can fly can teach us something about aerodynamics, so we can build better airplanes. Okay, I'm going to start by talking about the central puzzle, and which is the learning from the noisy real-world data. And then I'll propose my core model, the exception filtering phonotactic learner in my phonology paper, and followed by case studies in real-world corpora from English, Polish, and Turkish. Coming up, I will introduce my ongoing project, which I have written in my dissertation about alternation learning. It connects the phonotactic learning to the alternation learning. And then I'll discuss the impact and the next steps of this research program. So I'm going to start with phonotactic learning. We'll frame the problem of phonotactic learning from a computational perspective. I use those dots to represent the data sets, the data points that are available. The darker dots are those attested data that are available for children, and the lighter dots are unattested data that are not in the data set. Child language acquisition is what we call unsupervised learning problem. So the data set does not come with any labels. It's unlabeled positive evidence only input, which means every single word they hear, they don't know whether or not it is in the language or not in language. They just take it all in. I use the blue dots, the blue color to represent the grammatical sequences, and red color for ungrammatical sequences. Those are the underlying labels of grammaticality not available for children. The darker red dots are exceptions, like sphere, okay, or those exceptions in Turkish. So the learning objective is to arrive at a grammar that separates the grammatical and ungrammatical dots, okay, the data sets, whether or not it is already in the data set or not. And they will be able to predict the novel form judgments. Speed should be worse than a blick. Grammatical words should be better than ungrammatical words in acceptability judgments. Okay. So how do we do that? How do children learn to arrive at such a grammar? There's a baseline learning model. We just assume every attested structure is grammatical. Every single like sfa or blah, they're grammatical. And this is what we call the descriptive strategy, and we'll arrive at the tightest fit of the observed data set. Seems promising, right? But this will cause a problem called overfitting, which means the learning model has fit the observed data so well that it starts to incorporate those noise, like lexical exceptions, into the grammar. An overfitted model will fail to predict the unobserved data, such as the novel form judgments. And you see here that we assume that sphere is observed, so surfer sequence is grammatical, then we will not be able to predict that speed is actually ungrammatical. Okay? And this is a persistent challenge in modern days machine learning models, and also a challenge for linguistic analysis and child language acquisition. Children also have the problem to deal with this overfitting problems. I will say especially true for children because their data set is small, noisy, and unlabeled, so they don't have a lot of the information that are necessary for dealing with overfitting problems. And modern days, the most state-of-art phonotactic models, we usually use probabilistic models, but it turns out the problem of overfitting manifested in the probabilistic models. Right, this is one of the approach that we used I have also, as a practitioner myself, I've also proposed models that combines the probabilistic grammars and probabilistic inferences, like maximum likelihood estimations. Okay, we have a set of weighted constraints, and then we optimize over those weighted constraints using maximum likelihood estimations. And as you can see, it's pretty much a probabilistic version of the baseline learning model. So ungrammatical, every single observed data will be incorporated into our learned grammar. Another issue with our baseline probabilistic grammar is that it will conflate the grammatical and ungrammatical sequences onto the spectrum of real value probability. So everything, you cannot no longer draw the line between grammatical and ungrammatical sequences, okay? Because everything, including the lexical exceptions, receive a non-zero probability. And as a matter of fact, the most state-of-the-art, the benchmark model in Hazen-Wilson's paper, it requires the experts to manually remove those lexical exceptions before any simulation. So this approach is what we call data engineering approach, is neither scalable nor explanatory for child language acquisition. Children, they cannot look up online, Google whether or not a word is in their language or not, right? So I figure out the solution to this problem, that is to figure out the exceptions using the categorical grammars. The categorical grammars, compared to probabilistic grammars, it assigns discrete grammaticality labels. So it can be Boolean values like 0 and 1s, or multi-level values like 1, 2, 3, 4, 5, like in the Likert ratings. The benefits of categorical grammars is that it's ideal for children's categorical judgments and over regularizations. This is actually beyond the phonotactics. We found that children tend to learn a discrete rule or constraints and apply it everywhere. That's what we call over regularizations. You found it in the past tense in English, or for example, when children learned that you can add an ed to a word and then turn it into past tense, they will apply it to many other verbs, but they never over irregularize those lexical exceptions. Like you would never, they would never generalize the irregular pattern like go to becomes went and use it in other words. Categorical grammars also helps us to define the problem of lexical exceptions. Now we can just assign a discrete label 0 to every single ungrammatical sequences, and exceptionality emerges naturally from this discrepancy between the attestedness and grammaticality. So it also enables the filtering mechanism that we found in behavioral experiments. For example, in Lenz and Gahe, they found that participants they use their phonotactics to filter out the second language input in their perception experiments. So when you hear Spanish sentence, for example, with Japanese words in it, they will use their phonotactic knowledge to filter out those second language input like Japanese words. So categorical grammar also, I will argue in this talk that they're compatible with the variability and gradient acceptability, which has been shown in many previous works. There are another crucial components of the phonological learning in the presence of lexical exceptions, that is the frequency information. We found a strong correlation between the type frequency and the acceptability judgments. This is one of the lessons that we can learn from the probabilistic approaches. There's a significant correlation between those frequency and the well-formed judgments. You can see, for example, the schma, it has relatively low type frequency, and you also have relatively low acceptability judgments compared to the pla. It also exists in Turkish. So we found that the Disharmonic sound sequences usually have relatively low type frequency, and harmonic sound sequences usually have relatively high type frequency. They'll have the same values here. And there has been research showing that frequency information is utilized in the child language acquisition. So a big question for me is try to figure out a mechanism that is using the frequency information to infer the grammaticality while also utilize categorical grammars. So how do we do that? Okay, that comes to my model, which is the exception filtering phonotactic learning. Okay. I'm going to walk you through the workflow for designing learning models. How do I design any learning algorithms, especially for those human language acquisition? First, we need to figure out the structure of the hypothesis grammar. How does the grammar predict the grammaticality of a string at all? How do they compute those grammaticality? And the second component is the hypothesis space, which is a set of all the possible hypothesis grammar. You can conceptualize the problem of learning as selecting hypothesis grammar from a set of hypothesis grammar, the hypothesis space. And how do we select them? Well, that's the third component, which is the constraint selection criterion. It tells you the conditions necessitate the addition of a constraint to a grammar. How do you select a grammar from the hypothesis space? I'll walk you through it one by one. Now, the structure of the grammar is called a tier-based strictly to local, okay, or 2TSL. It says that it search for the structure of two factors, which is similar to two bigrams. Okay? It's the adjacent sound sequences of length 2. Like if you have a word, spigen, the 2TSL grammar will search for first surfer sequence and then move to the next bigram or two-factor, then FI sequence, and then keep going. Okay? And it will select all the two factors. What 2TSL grammar says is that if any two factors in a string, like spigen, violates the grammar, right? Like for example, the grammar here, we penalize SF sequence over the segmental tier. Then this word is ungrammatical. If you violate the grammar, then it's ungrammatical. Now, if we want to capture those non-local dependencies, in 2TSL grammar, we will project a tier, a non-local tier based on certain, for example, phonological features. I can project like ER sequence on the vowel tier. And the 2TSL grammar here, it penalizes any ER sequence over the vowel tier, so we'll penalize the string spigen again. Those tiers, it can either be learned from the data set, as Adam has explored it in the past. It can also be pre-specified by the experts. So in this talk, we're just going to assume they are pre-specified, but the learning algorithm for tiers is a future direction. Okay. Second components, the hypothesis space. Well, why it's so important is because if imagine I ask you to search for any random numbers without specifying a scope, there's no way you can figure out what number I'm thinking about, right? Because there are infinite possibilities out there. But if I narrow it down to, for example, the integers between 1 and 4, the problem instantly becomes easier. There's only 4 possible numbers to search for. Similarly, in the learning process, if I ask you to search for any structures without specifying the scope, it will be an intractable learning problem. But if we narrow it down to two TSL constraints, then the problem instantly becomes easier. The way we select the hypothesis space is to utilize the power of formal language theory. Formal language theory, it provides the mathematical tool to describe the shared properties of seemingly unrelated phonological generalizations attested across different languages, or you can call it in the typology. So for example, we found that most, well, a large number of phonological generalizations can be categorized in this very small region called 2TSL, like the Turkish vowel harmony, or Navajo sibilant harmony, or the English and Polish onset phonotactics. It captures a large amount of local and non-local patterns in phonology. Okay? And this class is formally restrictive, but also typologically robust, and it comes with very nice learning properties. It comes with efficient learning properties compared to more complex classes like context-free or context-sensitive, which captures patterns like nested embeddings in English, that's the syntax, and crossing dependencies. Those patterns, you never find it in phonology. You never find a nested embedding in phonological patterns, right? So to summarize, a good hypothesis space should be restrictive, but also typologically robust, and it comes with efficient learning property. There's another benefit for using 2TSL, which is that we have experimental evidence for 2TSL as a hypothesis space for phonology. It's supported by artificial grammar learning experiments. When we have nouns words, we have experiments with 2TSL grammar compared to more complex classes like the bigger regular class, participants find it easier to learn 2TSL grammar than a regular class. And it has achieved success across various frameworks, not only in my model, but also in many other probabilistic approaches. The third component, the constraint selection criterion. Here I use the classic OE criterion as the constraint selection criterion. So O represents the observed type frequency, which means the amount of unique strings that violate the constraint in the observed data. So highlight the observed data, the O. The expected type frequency are those strings that violate the constraint, but allowed by the current grammar. So highlight the current grammar. So the OE ratio, when it's lower than 1, that means the O is smaller than E. It indicates the potential constraints in our data set. So this criterion dates back to Trubetskoy 90 years ago. But now I have refined the classic OE criterion in this project. I'm going to explain it using this toy example, the no CC language. It penalizes any adjacent CC sequence in a language. The data set is a toy data set with 5 grammatical strings that and one exception, that is CCV, which violates the no CC constraint. So the idea is the learning model should learn a grammar, right? And then we will compare the results with the target grammar. Now we know the answer is the no CC constraint. So we'll see if the learning algorithm can figure out the no CC constraint from the toy example. So learning algorithm works like this. We'll first read the data set and then initialize hypothesis space, which is empty, which is 2TSL constraints, and the hypothesis grammar, which is empty. We assume everything is allowed before the learning process. There's no constraint in the hypothesis grammar. After that, we'll select a threshold from sending scale. Let's use the example 0.5 and 1 here. I'll explain this in a minute, okay? But you select the threshold to for the constraint selection criterion. The reason why it's a sending scale is because we want to prioritize those constraints that meets the lowest threshold. We first select the 0.5, okay? And the next step, we'll compute the OE ratio for every constraint in the hypothesis space. This is done by following this equation calculation here. For example, the O is the strings that violate the constraint in the observed data. The observed data has only one string that violates the CC constraint, that's CCB. So O of CC is 1. The expected rate frequency of CC is computed using this complex equation. I don't want to explain details, but basically it's strings that violates the constraints but allowed by the grammar, divided by the strings that are allowed by the grammar, which you can just count them, 3/8. Right? There are only 3 strings that violate the constraint, no CC, but allowed by the current grammar, which is empty. Okay, empty grammar means everything is allowed. This process can be facilitated by the shortest distance algorithm using the Painini library. All right, so after we calculated OE ratio, the next step is to compare the OE ratio with the selected threshold, and we found that CC constraint, it has OE ratio smaller than the selected 0.5. So we will put them, add it into our grammar. We add this constraint with OE smaller than the threshold to the grammar and filter out those strings that violate the grammar from the data, that is CCV. Add that to here and filter out the CCV from the data set. After that 3 steps, we go back to the second step and do that all over again. We recalculate, reselect threshold as 1, recalculate OE, recompute and update the grammar and data set until the thresholds terminate, until learning process terminates, until we exhaust all the thresholds from the ascending scale. And we will select all the possible constraints in the hypothesis grammar. Okay, and you can see here, we started with the empty grammar and we ended with no CC constraint in the grammar. We learned a grammar from the toy example with an exception CCV. Now, I'm going to apply it to real-world corpora, English, Polish, and Turkish. I'll compare my model with 2 other models. The first is a baseline learning model, which has the same hypothesis space, the 2 TSL grammars. It also uses the categorical grammar, but it doesn't have any statistical criterion. Instead, we use this baseline criterion we have talked about before. We assume every attested sound sequences is also grammatical. And the second is my model, the one with OE criterion. And the third is the model that utilized the probabilistic approach. We use probabilistic grammar, and the MLE comes with it. And the end goal here is to understand the role of exception filtering mechanism. Okay? There might be more powerful models, but the reason why I choose these is because they have the minimal difference between them and my model. All right, let's first look at the English. The data set is from Hayes and Wilson's model, the paper. It's basically the intersection of CMU pronouncing dictionary and the SELEX2 dictionary. And there are a large amount of onsets with their type frequency, like blah, shra, and all their type frequency, which means the unique strings with those onsets. It's relatively clean. So basically, it's a model that a baseline search algorithm can work. The test data has 96 novel form with the onsets and the tails. They're all fake words. And the experiments works like this. The listeners will listen to those novel forms and they will rate it out of 5, the recur ratings. And then the researchers, Dallins et al., they averaged the recur rating over the subjects. So you see those decimals, 4.5. but they actually like individuals, they have categorical judgments like 1, 2, 3, 4, 5. Right? And the evaluation is that we'll let the learning algorithm to figure out the learned grammar, and then we'll compare that grammar with the human judgments. Okay? We assume that humans use their own grammar, the learned grammar, to predict their acceptability judgments, right? And compare the machine judgments with the human judgments. Okay? We'll use the correlation test to do that. Here are those detected lexical exceptions this I've shown you earlier. Okay, we basically found all the exceptions in the learning after we learned the grammar, and all those onsets they receive relatively low acceptability in novel forms. And here's the result of the correlation test. Let's first compare the exception filtering algorithm with the baseline learning algorithm. They are basically the same. Because this is a relatively clean data set and the exception filtering mechanism doesn't really play a role here. But you can also find that Hayes and Wilson's model, you achieved relatively high score than every other models. So it's a very good model. But my question is, what about we apply these models to noisier data? I'm going to use the noisier data here. So the Polish data set, it also has a large amount of onsets. It's from a child-directed corpora. And the test data consists of the novel forms. There's the simile experiments, have the human judgments of novel forms. And then we found that the let's still first compare the exception filtering learning model and the baseline learning model. Without a exception filtering model, the baseline learning model has not achieved as high performance as the exception filtering model. And also we found the Hayes and Wilson's model is also outperformed by the exception filtering model. And what about noisier data? Let's take a look at the Turkish data set. So use the Turkish electronic living lexicon, which is a large corpora with a large amount of forms, both derived forms and also roots. It's extremely noisy. It has almost every attested sound sequences, every attested vowel sequences is, sorry, let me do that again. Every possible vowel sequences is attested in the corpora, right? Everything has at least 17 type frequency in the corpora. It's extremely noisy. The testing data is also those novel forms with approximated judgments from behavior experiments. Okay? The evaluation is the same. We use the correlation test, and there's no score for the baseline learning model. The reason is because every possible vowel sequence is attested, so everything is grammatical in the baseline learning model. Everything is 1. So there's no standard deviation, and that's why there's no score for the correlation test, which relies on the standard deviation. And when we compared Hayes and Wilson's model and exception filtering model, we found that without the exception filtering mechanism, Hayes and Wilson's model is outperformed by the exception filtering model here. I think beyond the statistics, another benefit of the exception filtering learning model is that you can interpret the learned grammar directly. To the left is a feature chart with all the features that captures the vowel system in Turkish. It's a beautiful vowel system. It's symmetric. Right? And we use 3 features to capture that vowel system. To the right are those vowel sequences. Leftmost column are the first symbols, topmost column are the second symbols, and I use blue colors to represent grammatical, zeros represent ungrammatical. You can see that here. I'll walk you through it one by one. So first we learn those backness vowel harmony. Every single vowel sequences with different backness feature is penalized. They have 0 score. And we also learned the roundness harmony and also some mid-val phonotactics. And when we can compare that to the documentations in the past, we found that they're very similar. So we can also use this learning model as a tool for field workers to analyze their languages in the future. To recap, the evaluation has evaluated the models in 3 dimensions: the ability to predict novel form judgments, the scalability to new data, new languages, and interpretability for direct investigations by phonologists. And I think the exception filtering model has achieved a success in 3 dimensions. Now, I also compared the results, the learning results, with the Hayes and Wilson's model, and we found that as the amount of lexical exceptions increase, the performance of exception filtering model becomes comparatively better and better. Right? I computed those ratio of exceptions using the amount of detected lexical exceptions by the exception filtering model. And the lesson we learn here is that first we need restrictive hypothesis space for the learning in the real world. And you see that all 3 models that use the restrictive hypothesis space, and they're all very successful, right? When it comes to very noisy data set, you need an exception filtering mechanism. And this is based on the empirical evidence that there is a frequency grammaticality correlation. And I use that information in my model that combines the strength of the categorical grammars and the statistical criteria. Okay, now I'm going to connect the main proposal of phonotactic learning to the ongoing project of alternation learning. I don't know if we'll have enough time, but I will go very quick in this part. Okay, so in the past, in phonologists, we usually model the phonotactic and alternation learning as completely different modules. Usually, okay, there's a comments. Sorry, I go back. So we usually model in a completely different modules, and usually don't think about phonotactics and alternations at the same time, right? It's like there's no connections between them. And my ongoing project try to find how does the phonotactics can facilitate alternations. So first, we found in experimental evidence for these connections. In artificial grammar learning experiments, we found that phonotactic, when learners are learning their alternations that are contradicting the phonotactics, they will have some difficulty compared to alternations that are supported by phonotactics. I'll give you an example here. Imagine I'm teaching you a phonology course. Right? I'm giving you the data set here. And I ask you to figure out the vowel harmony pattern in Turkish with those exceptions. There's no way you can find a good answer, you can find a good analysis, because there's always the exceptions that contradicts any analysis you have, right? But what if I use phonotactics, give you a hint, and filter out those lexical exceptions, and the problem instantly becomes easier, right? And that's what we do as a teachers, and we do give students the clean data set. So my idea is that the learners can use phonotactics to do that too. We will filter out those exceptions, use the phonotactic learner, and then proceed the alternation learning. I call it the 2-stage phonotactic alternation learning model. It's a unified learning model with 2 different modules. And alternation learning can be extremely easy because heavy lifting has been done in the phonotactic learning process. Okay, I will go very quick. The alternation learning goes like this. We'll take the input data and the learned phonotactic grammar from the exception filtering model, and then the data set the learning model will extract those segment-based mappings. Okay? So for example, the Turkish data I've shown you, we will just extract those phonological mappings from underlying representation to surface representation as we do in the 201 linguistic course. And then there is a context of each phonological mapping from UR to SR. We extract all those mappings. Oh, by the way, this is also called the 2TSL functions. We can talk about that later. And the next step is to filter out those exceptions from the data, from the extracted mappings. We're using those learned phonotactics. We have the no RA sequence in the learned phonotactics. Then we'll filter out those context R after, sorry, context R before the right? We'll filter it out from the context. And then we will extract the feature-based generalizations based on the filtered data set. We just posit a rule if there's no exceptions. It is very similar to traditional phonological analysis. And then we will learn those rules like A becomes front after front. Okay? A becomes back after back. And then we output the learned rules. It's a very simple model. I'll apply this learning model to Turkish data. It's a child-directed corpora with relatively small amount of forms. We'll split it into 10 folds and we'll input the training data incrementally. We'll give the learning model the first 10% and then the 20% and test it on the rest of the testing data set. Okay. And here's the result. I compared my learning model, the red line here, with the previous models. There's a transformer-based seek-to-seek model, which is trained in the Caleb Bell's dissertation, and he has his own model too, which is the Bell's 2023. His model also learns a rule like this. A underlying form becomes a back after back, front after front. And we found that our model both outperformed the state-of-the-art transformer-based model. The reason is very simple, is because the transformer didn't have enough data. Okay. This is the strength of the model that we use, the rule-based learning model. And we can succeed in relatively small data sets, and especially those are available for children. Another insights we found in the learning results is that there's a correlation between the phonotactic learning and alternation learning. When the phonotactic learning fails to learn certain constraints like RA sequence, you also fail to learn the alternations that are related to that phonotactics. So, for example, RAs will cause that the learner fail to learn the backness harmony feature pattern. And when the phonotactic learning succeeds and achieve a high accuracy, the alternation learning will also be successful. And recently I've tested the model on Finnish vowel harmony, and it has also shown a similar learning results. Another cool thing I found in this project is there's implications in language change as well. So this is a quote from Kiparsky, is that language change is a natural lab for learning algorithms. Every learning algorithm has a diachronic predictions. So my learning model predicts that when language contact happens, there's increased amount of exceptions in the lexicon, and it will cause the loss of phonotactic restrictions. We will not be able to learn certain phonotactics because the amount of exceptions exceeds that thresholds in language. And then the phonotactics will cause the loss of productivity in the alternation learning. And we observed these kind of language change in many other languages, like in Korean, the Middle Korean to contemporary Korean, there was a loss of vowel harmony pattern. Okay, there was a ATR harmony in the Middle Korean, but as there are more and more loan words borrow from languages like English, where you see the loss of productivity in both the phonotactic constraints and alternations. My learning also predict the timeline of phonological acquisition. We found that in child language acquisition, children, they learn their phonotactics earlier than they learn the alternations. We found that phonotactics is learned as early as 6 months, less than 8 months, and the alternations is a little bit later, like 12 months is the learning of the perception, and the 2.5 years is the learning of the production of alternations. Okay. That's the summarize the whole talk. I found the importance of the restrictive hypothesis and exception filtering mechanism in this research project, and the learning model was successfully acquired the interpretable phonological grammars with the lexical exceptions identified in the real-world corpora. In the future, I plan to extend this research project to incorporate other factors that influence the acceptability judgments to improve the model performance. So formal language theory, as well as my model, it says nothing about lexicon or performance factors, right? And my learning model, they learn a grammar and predicts a grammaticality labels. And there's also other factors that combined with the grammaticality that influence the acceptability judgments, such as the testedness. So one thing you can do is use statistical models to combine the influence of different factors in the, for example, linear mixed effect model with the testedness in the lexicon and the grammaticality as the main factor, and the other performance factors as random factors. In today's computational phonology, there are two main different circles. The first is called the mathematical underpinnings. We focus on the mathematical foundations of phonological patterns. We try to characterize phonological generalizations using tools like formal language theory. And there's also another group, which is the computational modeling group, which models the behavioral data using the real-world data. In my research project, the entire program, I try to combine this to incorporate insights from both circles. And I believe this is where our field is going forward. It's a beautiful marriage between these two different circles. Okay, I'll end this talk with the outlook. So I plan to spend a large chunk of my time to refine the learning algorithm. We test the alternative hypothesis space and the other noise filtering mechanisms, and refine the alternation learning algorithm. And I also only apply my model to a few child-directed corpora, but there are many other corpora available. I will try it too. There's also a plan to provide a proof of learnability of my learning model. Now we only have tested model on 3 different data sets, but you can only test so many data sets, right? But the proof means you can prove that the learning model can be successful in any data sets. The proof is very difficult. I will explore novel empirical domains like tonal phonology, and also, as I mentioned earlier, you can discuss the implications of language contact and change in my model. I want to connect my model to the general machine learning community, especially there is a general problem called anomaly detection in machine learning, because the exceptions or noise is not only for language data, but also exists in many other forms like image and videos, etc., or misinformation we found online. I planned to collaborate with psycho and neurolinguists to provide more evidence for the computational models that I proposed as well. And I want to emphasize that this research project is only at its early stage, but we are making incremental progress every single day. Right? I will end this talk with the call. Let's harness the power of computational models to advance our understanding of phonological learning and beyond. That's the end of the talk.
All right, very much good talk. Well, now to questions from the committee. We'll start off in order of geographic distance. So Richard, I'm going to ask you questions first. You can hear me?
Yeah, I can hear you. So I do have a question about the procedure. So are we also gonna have questions in a private session or only public questions?
Oh, yeah, we'll have
You have to go here, I guess. Can I hear him? Can you hear? Can you hear? Oh, okay. Oh, go ahead.
We'll have both.
Okay, yes. I have some more detailed questions that we can save for later. But let's see. I actually have a lot of questions. Let's see. I'll ask two of them now. So first is about your use of the term grammatical,
Right.
And the claim that exceptions are not grammatical. It seems like that's not quite in line with standard use of the words. So an irregular verb is grammatically correct, even if it's not productive. So do you think your idea of grammaticality is actually just productivity of a rule? Or do you really want to claim that the exceptions are, in a strong sense, ungrammatical?
Right. I define the grammaticality in a very strict term, so I kind of changed the semantics of it. So I mean, if it's violated by if a word violates the grammar. If it's ungrammatical, that means it violates the grammar. If it's grammatical, that means it does not violate the grammar. So I changed it's not the usual use of the word. I don't think it's a good idea to change it though. If we change it to productivity, there are some issues with the term of productivity of phonotactics. So there's like, it's hard to say a phonotactics is productive.
Well, if you were to take your definition and expand it into the world of morphology, wouldn't that predict that when I say like I went to the store, in some sense that's ungrammatical because the past tense of that verb is an exception?
Huh. Right. That's a good point. It violates the that's a good point. So there is a terminology issue, right? But I think in my work, it's a good idea to use the grammaticality as strictly to the grammar. It's just a label of what we are doing here. But if you have other suggestions, I would like to hear it. Productivity is not the best way to say, I think.
Okay, yeah, it seems like grammaticality is also a bit problematic.
Yeah, I have got that from the reviewers as well, but I just couldn't find a better alternative.
Okay, yeah, okay, okay. I have a second question, which is about so your model is fundamentally about balancing this tension between storing everything as exceptions versus trying to model everything using rules.
Yeah.
And I'm wondering, like, what are the key parameters in your model that control that balance and that trade-off? Like, if I wanted to have a learner that's going to store more stuff as exceptions, or if I wanted to have a learner that's going to try to model more things using rules, what parameters would I tweak in the model to get those different outcomes?
Huh. How do you store more? Can you elaborate a little bit on the
So
store?
the model has a number of free parameters such as the threshold schedule,
Yes, yes.
and different settings are going to lead to different outcomes in terms of how many things are counted as exceptions versus how many things are modeled using productive rules.
Right.
And yeah, I'm wondering if you could comment on like, well, what are the key parameters that affect that balance?
Um, I think you mentioned it, right? So the threshold itself is the key, right? So it determines how many lexical exceptions you want to store in the learning process. So the higher the threshold is, the more exceptions will be stored in the lexicon. There are some proposals, like there are Charles Young's tolerance principle saying that the larger the lexicon size is, the more lexical exceptions you should have. And there is the famous, I think I have a slide, but there's a logarithm in it. So I think this is it eventually comes down to an empirical question, like whether or not there is a cognitive tipping point that he will put it in our brain that will say, okay, I will allow so many amount of lexical exceptions, and that's it. But I don't know. I don't have an answer for that.
All right. I'll yield to the next committee member.
All right, thank you. So when you use follow tactics to mark exceptions, working at a point where you're not dealing with morphological segmentation.
Right, right.
So what gets marked as an exception is a word.
What marks as an exception as a word? For the phonotactic learning model, right? Is anything that violates the existing phonotactic.
Right.
Yeah.
No, the point is, it's a question of, when you store exceptions, what exactly is it that's stored? So the point being that suppose we had
I got it. Right.
Which is disharmonic and gets stored as an exception.
Right.
Was that one which also admits affixation of variables?
Yeah.
Each of those forms, must each of them independently get identified and stored as an exception.
So I assume that it's a whole word storage. So both the roots and also the derived forms are stored in the lexicon. There is also theories says that you only stores the roots and then you derive the forms using the grammar. I haven't seen the consequence of that in my model yet. I don't know whether or not that's going to be an issue. But I just assume everything, the entire word, if it's violating the phonological grammar, we'll store it in the lexical exception.
Yes, what that
So
brings us to mind the possibility that, you have a word stores an exception.
Yeah.
And then you productively combine that root with a different affix.
Yeah.
That's not what's stored. Therefore, the harmony would get applied productively to the root. It's not the root that's marked as exception.
Yeah.
It's the entire word.
Yes, I think so. But not every word. So that's why we're using nouns-word experiments, right? So you can still test the grammar without referring to the existing word. And you will not extract that. You'll not be able to extract that from the lexicon because it's novel form judgments. I think it comes down to, I don't think it really matters in my model, but
well, I'm just thinking of the grammar that result. I predict that productive novel forms would be regular.
Yes, exactly. Yeah. I will think about it, but I think you're right. So you're right. So if you have whole word storage, then you cause the problem that the learning model will apply the rules to those roots and contradict the lexical exceptions stored. I have to think about it. That's a great point. That's a great point. Yeah, I haven't thought about it yet. I think morphology is definitely something I haven't done much about, but there's a huge room for explorations. And yeah, go ahead.
This is also looking at the active learning. Start with the given criterion for all the constraints. Ratios.
Yeah.
The criterion and adopt them.
Yeah.
Is it, have you thought about, or is it possible that if you adopted one of them and then use that grammar, one constraint adopted, that could affect the recalculated ratios for the other constraints?
It does. Yeah.
It does. Okay.
Yeah.
So is there a strong reason for at one point adopting all the constraints that at that point have their calculated only below the criterion, as opposed to say, pick the constraint with the lowest ratio, so long as it's below the criterion. Not that, and then with that grammar, recalculate everything else. Look at the newly recalculated lowest ratio.
Yep, that's my my beta version of the learning model.
Okay.
It also works. It also has achieved similar results. But I think eventually it becomes too slow there, because you have to do it one by one, right? You have to add the lowest constraints, and then you do that again. And for all the 400 constraints, I have to do it one by one. I think it's also possible. It's also I think it's when you find a balance between the engineering and the science. But yeah, that it's possible. I think I would rephrase this. So my model, it has this very complex ascending scale and the thresholds. There's also one possible way to do it is you select the constraint with the lowest OE ratio, and then you just repeat the loop of recalculating the OE and selecting constraints. But that approach, it was not efficient enough in my computer. It takes like 10 years to finish all the experiments I have done already. So instead, I choose the more practical one, which means that we will select a bunch of constraints with lower than certain thresholds of OE, and then we'll recalculate the whole process.
So the computation really goes up.
It really does. It really does. Especially I realized that when I was working on this project, there's many research projects they avoid to do the simulation of the entire language. And then I realized why. Because like imagine I have 38 segments in the language, consonant and vowels. How many combinations do you have? And if every single combinations it takes 1 minute to run, that's like an entire day just spent on the simulation. So yeah, there are some technical issues. Maybe you can find a solution in the future to speed up this process.
Well, not that it's somewhat trivial, but it's sort of suggesting that sort of the linguist approach would be remaining with the pure every segment is an island to itself approach from the outset. We look for motivated classes.
Yeah. Yep.
So that picking one constraint would be a class of things that applies to be managed by a whole bunch of different individual children.
Oh, Connor is here. So yes, I think natural class is also a good idea. For me, we can talk about that later. Natural classes, yeah, there's also some.
Yes. So,
so can you go to slide 59?
Okay. Here we go. 59. There.
Yeah. So, I'll return to Bruce's question about integrating morphology. So if you look at the exceptions here, the exceptionality is present both within the root and across the root affix boundary. There, in Turkish, there are roots that are exceptional that are harmonic within the root, but are exceptional across morpheme boundaries.
yeah.
And so I just wonder, what do you think if rather than taking whole words, like if you had just root internal access, like is everything harmonic in the root? If you took that approach where you were just looking inside roots for this alternation learning, would that change things? And do you think the fact that there's already something within the morphological root can serve as a cue to an alternation learner to say, hey, I already see when I'm looking at the root, this is funky. But there's something weird about this. Because I've got E followed by or I've got in the last case, I've got O's in all syllables rather than O just in the first syllable. Can those cues get integrated into a model so that they're cued the same way that I imagine a learner would be cued by saying like, hey, that root's funky. If you give me that in a not word test, a word test, something like that, I'm going to automatically begin thinking like maybe this doesn't work like the regular stuff.
Right. So this is actually very complex, right? Every time when people asking the two-stage learning model, like you have two things you have to ask. Like, are you asking about phonotactic learning or asking alternation learning?
I mean, that's the beauty of being on the committee. You can just pick and go with it.
Right.
You know,
So
it can be vague. You have to be.
I'll ask both. I'll answer both. So the learning of phonotactics usually assume is earlier than morphological analysis. I'm giving you the answer from an empirical perspective, right? Before we do any engineering, like technical stuff. So empirically, children, they learn their phonotactics as early as 6 months. It's before they learn any lexical informations. So, and we know that learning morphological rules, it needs some kind of lexical information. So you need to know what each suffixes corresponds to, right? And you know what is a plural. Six months old babies, they don't know what is a plural morpheme, right? So that rules out the phonotactic part. So definitely in phonotactics, we don't care about the suffixes. We don't store the whole. We don't know how to segment roots and suffixes. So the learning of the morphological information must happens in the alternation learning part.
But, you know, it's not just like babies then fully grown adults. Like
Yeah.
there are stages to the
Yeah.
learning process where at different points along the way, kids
Right.
have different access to this information and, you know,
Yeah.
draw from both of these, but they're not doing it perfectly well.
Yep. So the phonotactic learning, I actually didn't mention this. It starts early as 6, but it continues until they become adults. So it's so I think you're right. I think you're right. I think you're right. Yeah, I think you're right. In the future, we can probably try to find a model that incorporates the morphological information into this part. Yeah,
I mean, I guess my thought is if you did something like this, you would presumably predict a difference in the learnability of exceptions across morpheme boundaries that also have exceptions within the roots versus things that are regular in the roots but exceptional across morpheme boundaries.
yeah. We'll talk about that. Yeah,
I have
there's-
one other question. So can we go to the comparison with belt and central that?
Okay. Here. There we go.
This is where. So were each of these three models doing the exact same task?
Yes.
Exact same thing, because I thought one of them in the dissertation you indicated that one was learning URs as well.
Oh, that's a great point. So in my model, I assume the UR was given. So we know what's the UR of the testing data. Right. So the testing data and also learning data, actually. So it actually makes a huge difference whether or not you have a UR or not.
For learning URs.
So Belf model, it learns a UR. It has that's why it has this very low score in the beginning. Okay, this is actually a graph you have to dive deep. So this graph means as you increase amount of data available for the learner, the performance of the Bell's model becomes better and better. And think about it, it makes sense because his UR model, it requires the contrast between it requires the amount of information, like different allomorphs. So you want to learn a UR, you must know what are the possible SRs. Right? But if you don't have enough data to see all the SRs, there's no way for you to infer the correct UR. And that's why his model was underperformed in the beginning.
So is it a fair comparison to compare your two here?
It's so that's why I didn't claim my model outperformed his model.
But the visual suggests that
Did it?
it's like if
I can-
like they belt model the pizza boxes and they're like a race.
Uh,
They're gonna be faster. Because they have a harder depth.
Yeah. I actually in the dissertation I mentioned this, so I said like there's a reason for his model didn't do so well. Yeah. But we definitely so the transformer model, it doesn't learn an UR. It also is underperformed. So I guess that's the worst model in any cases.
And that's what we care about trashing. Right?
Yeah.
My turn. So since this is the theme now, I'll ask about this too. So like starting off from Bruce and Athens. So one, it's correct to say that. So for your alternation learning, the learner that's learning the process itself doesn't do any like it doesn't have the capability to identify exceptions.
No.
All of the identifying of exceptions happen in the level.
Yep.
So in a sense, like you're saying that there is no such thing as a like inherently process like alternation based
Yeah.
exception.
Yeah.
Is that correct?
In my model, yes. So I don't have that. I don't have that, but there might be such a mechanism in the alternation learning process.
Yeah, absolutely. Because I think what the prediction is, I think the prediction that you make is that that phonotactically licit forms should never be exceptional with respect to alternation.
All right.
I guess I should phrase that as a question. Is it a predictive model that phonotactically licit forms will not be exceptions in terms of the processes? And if so, is that I believe that could be problematic, like, because I think we probably go through the Turkish and find like groups that are phonotypically licit, but don't participate in altercation. I guess your learner would learn that if it sees the alternating forms, but it wouldn't see that, or it would see that as at all of the morphological form. It only saw a form in the. I guess this is what Bruce was asking.
At least in Turkish, I think we found this very nice isomorphism between the phonotactics and alternations. Like we don't, right? Like that's why the model works. So if you do see those kind of cases, you will find the model doesn't work. That's it, right? Yeah.
It's two R's in the root. There's nothing exceptional about two R's. But when you question more, but it becomes front in suffixes. So it's not like it's disharmonic within the root.
Yes.
But it's only disharmonic across the morpheme boundary. So if a kid only had access to the root, they would like, if like when they're little, that no one's telling them it on the watch or whatever.
Wait, so let me clarify real quick. So do you like apply that productively, like the tab?
So if we're gonna connect this to my question.
Yeah.
Can you go to the line where we all the
Yeah, this is, I was looking forward to this.
So, in this case,
Yeah.
yes, it looks like an exception, and it is an exception, but there's also another layer on top of it. So people at Rutgers University proposed that these, I mean, it's also apparent phonetically that these final L's are interfering
Uh-huh.
with Backus harmony.
Right.
So, in essence, my question is, will your model be able to capture like multi-layered stuff that looks like exceptions, but in the end, they refer to systematic, phonological, or phonetic
Yeah,
regularizations? In this case, even though it's the final low is up,
Yeah.
the L is clear, so we have different L in Turkish, dark L and clear L, so it's CEI.
Yeah.
So on the surface, I can hear that it's a plural or palatal L that interferes with Backus harmony. So can your model capture the ease of articulation, or maybe the two articulators being close to one another, so that this
Yeah.
is the easiest way of producing or uttering?
I actually, my committee will know this. I actually was working on a similar data set, which is the Hungarian data, vowel harmony. It also has the other segments. It kind of plays a role in you can use it to predict the vowel harmony patterns. So my model, massive answer that first, my model cannot do this. Like my model failed miserably in that. It failed miserably because those, it, I think there's two reasons to explain this, right? So one is that the vowel harmony patterns, the regular ones, has lost. So those exceptions, there are so many, so there has affected the acquisition of the vowel harmony itself. So those lexical regularities, they are internalized not as a part of the grammar, but there's some kind of lexicon-based regularities there. It's not productive to everything, but it's partially productive, right? So the first explanation is the loss of productivity. The second is there are other mechanisms in our grammar. That's what Bruce Hayes and colleagues would suggest. So you have not only a rule-based system, but there's also stochastic. And there's the probabilistic models. We'll come back to where we come from. So there's the stochastic models that takes into various factors like what you have said. You can make it for example, constrained, weighted constraints that will play a role in the acceptability judgments. So, two possible ways to do this. Explain this. Okay.
And I'll just ask one more question. So, when talking about the, in order to take your alternation learning model, bring up work by Adam Chong and other people,
Right.
that point, that show experimental evidence that suggests that phonotactic learning directly plays a role. And you argue that your model works in the same way, but there is a crucial difference, right? That they are like in Adam's work and Peter and Tessier, et cetera.
Yeah.
Constraint-based framework where they say, look, we're going to learn the learner learns the constraints, and then learn some markedness constraints that describe tactics, and
Yeah.
those same markedness constraints are then leveraged to explain the alterations. Correct me if I'm wrong, but in that work, they're not looking at exceptions actually.
Yep.
In the absence of exception,
Yeah.
phonotactic learning plays a role in the process.
Yeah.
But
Yeah. So
in your model, like to what extent are does the phonotactic grammar
like directly help out the process learner with it.
Yeah. So I was thinking about doing an experiment myself to kind of follow Adam Chang's research. But you're right that his work does not provide direct evidence for my model. Yeah. But he has, I think there are many different ways for phonotactics to facilitate alternations. I'm just suggesting one of them. One of them. Yeah. Adam Chang's research didn't use the lexical exceptions. I think future work, I think this is where the theoretical construction can enlighten or shed light on the future experimental work. You can try to do experiments like Adam Chang, but also incorporate some lexical exceptions in it.
Does anybody else on that? Should we do another round of questions? Or does the committee have more questions? Should we open it up? Richard,
There's
you have
stable
questions that you want to ask? You don't have to if you don't.
Yeah, I do have one more question, which is maybe following up on this question about what exactly is stored in the exceptions. Seems like the model here predicts that people could learn arbitrary strings as exceptions.
Let
Right?
me,
But that doesn't seem right because there are still maybe weaker phonotactic restrictions on things you can have in your lexicon, even if they're exceptional. Like I can have sphere in my lexicon in English.
yeah.
An English speaker can't even really pronounce something like spick. You'll have to add an epenthetic vowel in there. So there must still be some, like your model seems to have no constraints on stuff that can end up in the exceptions pile. But that doesn't seem quite right. Do you have any comments on that?
But why it's not right? Why we cannot
Oh,
have
because something like zbik is for like not phonetically trained English speaker is not even pronounceable. They'll have an epenthetic vowel that they put in there. Let's say zbik.
right? So if you haven't heard a word, then you'll not be able to store it, right? If you haven't,
Sure, but they might have there's lots of
ah,
foreign words that we hear, but we alter them before we store them as exceptions, it seems.
oh, okay, I see. Right. So if you have heard, yeah, so I think has been some theories, right? Like people will say there is a
Years,
decay
but
theory.
there was
Yeah.
thinking of Brzezinski was an important politician. Lots of people were in the 70s were exposed to that consonant cluster. Um, but I think most English speakers still would pronounce it Zbigniew. So
Um, there are some theories like it's called like lexical decay. Basically, you memorize some, you hear all the different words at an early age. If you, my parents used to play those like Mexican sounds to me when I was a kid, but I just didn't internalize those words in my lexicon. I forgot them, right? People can forget those lexical items, I think. So that might be one of the explanations
okay,
for the
and
yeah.
that's something that's not accounted for in the current learning model.
But yeah, it's not accounted by my learner. But do you know any alternative models that can incorporate those, set a limit to lexical exceptions in the language? I
I mean,
cannot
it
think of
seems like a case where some kind of more gradient Wolframinus measures would.
gradient performance. Right. I need to look into that. Yeah. I know their UCLA has a what's her name? Uh, I forgot her name, but yeah, she's working on something similar, something related to that. Claire, right? Claire Moore Campbell.
All right.
Right. Campbell.
Why don't we open it up? Check the whole room. Same.
Yes.
So. I think let's see.
Yeah. Yeah. I define noisier as there are more words that contradicts the learned grammar, which is validated by the behavioral experiments. So the learning models that I proposed, they detected those lexical exceptions, and we can calculate the amount of them. And then we can calculate the ratio between the exceptions and the size of the data set that it's trained on. And then we will know the amount of the ratio of exceptions in the data set, in training data set. But like the Turkish data set is extremely noisy because we found a large amount of exceptions in the corpora compared to the size of the data set. But you're right, right, there's the term noisy is very fuzzy. So yep. Yeah, go ahead.
Like what the, so the threshold. That particular person is. That's something that starts out with.
Right. Yeah. The thresholds. Here we go. So the thresholds, they are hyperparameters. So we obtain them using like post hoc testing. So basically we can run all the possible thresholds from the 0 to 1 in the testing phase, and we will just see which is the best parameter. This is done in Hayes and Wilson as well, and in my model. So we both just basically try many different things. Try 0.1, 0.3, 0.5, and then just say, okay, this is the best model we can find. Yeah. There are some other proposals like Torrance principle. It doesn't need that hyperparameter. Just say, okay, there's a bound for every languages. It's dependent on the size of the data set. Yeah, there we go. This is definitely an unsolved problem. Hyperparameters. Which good.
So my question is about the portability model. So as human beings, we have very subjective learning experiences when it comes to language. So what is grammatical for one person, in essence, should differ from another person. It actually is different. So is your model based on a hypothetical learning that captures all subjective learning experiences, or is just an ideal one single model that kind of mimics ideal learning of a language? For example, does it matter if I know more languages or if I'm raised in a bilingual environment? Is it going to affect any calculation, any processing?
It is. You're absolutely right. So in my model, most the computational work will assume that there is one target grammar shared by everyone. Everybody has the same grammar, and also assume everybody has the same data, right? We're training the model using this one data set of everybody. But you're right, like if it's a bilingual speaker, their data set might be different, right? The data set might be Turkish and English, right? So and you can definitely train your model using those different data set, and you get different results, right? So this is, I think, is actually a strength of my learning model. You can see the learning model learn different grammars from different data sets, and you arrive at different target grammar. It's just I only evaluate it on one data set, on like a idealized data set.
Can you explain how this works? So is it just a simple union of two language or grammar sets with some intersection or not? Or is it just a simple addition, or are there further constraints that regulates how bilingual mind can learn stuff?
Right. I don't have a theory on that, but it's like we can go from the beginning, right? The data set is one thing. It's one gigantic set of English and Turkish, let's just say that. And then the learning model is trained on that combination of two languages. You will learn one grammar, which is, I assume, is the Turkish overwhelmingly more in the data set. It's not like 50-50. There are more Turkish in the data set. And then we'll compare the results with the judgments of the Turkish bilinguals, right? Or when the Turkish kids grow up, and they'll predict the judgments of novel forms. And I haven't tested yet. I believe that we will find a high correlation between that and the prediction of my model.
It can also be extended to like speakers.
Yeah.
Interference from, for example, German Turkish people with the anaphoric use again. German rules are more active. So
Yeah.
the anaphoric potentiality comes from German influence. So there maybe your model or the good job.
It will. It probably will. I think comes to bilingualism, there is also a factor of L1 and L2 acquisition. It depends on what kind of bilingual we're talking about. If you are a kid who are born with two bilingual parents, that's different from someone who learned Turkish in the first place, and then when they become 3 years old, 4 years old, they start to learn English, and it actually is completely different. Like I actually think there is a probabilistic model will work much better when it comes to adult language acquisition. We can talk about that with Richard later. I have a hypothesis. It's like the learning of probabilistic matching is an ability that we acquire as we grow older. We become better and better probabilistic learner. When we are a kid, you're more likely to be a categorical learner. We'll talk about that later.
I think probably the question here, one should wrap up when it starts at 3.
Oh yeah, right.
At this point, I'll thank everyone for tuning in. And then we figure out. So the meeting will stay here, and everybody will leave. And
I also
meeting will be great.
need to leave.
Yes, you need to leave. We're going to talk in secret about you, but then I'll give you a text when you leave.
Okay, don't forget to turn off the recording.
Yeah. Somebody